Good afternoon, everyone. I'm Jian Tan, a PhD student in George Mason University Computer Science Department. This project is about pigment-based image analysis and editing. This work is partially done in my Adobe Research summer internship. Physical paintings are created using real-world brushes with some primary pigments, such as oil pigment, watercolor pigment, or acrylic pigments. These pigments are not RGB values used in digital software. They are not mixed with linear models. These pigments' color perceived by us are the result of a complicated physical model over light illuminant, pigment parameters, and human eye response. There is a physically inspired color compositing model called Kubelka-Munk model. This model takes pigment absorption, scattering, thickness, and substrate reflectance as input to obtain the pigment reflectance parameters, which can be fed into a standard imaging system to get final rendered RGB color of this pigment. The Kubelka-Munk model and the imaging system are both nonlinear transformations, can be represented by this Km function and phi function. The whole color compositing system is nonlinear. When we mix two pigments, the mixing of two pigments' absorption and scattering parameters is linear. However, the Kubelka-Munk model is a nonlinear color compositing model. Here we use thickness equal to 1 and canvas reflectance also equal to 1 when rendering these RGB mixing colors. Canvas reflectance equal to 1 means that this is white. When we visualize the continuous mixed RGB colors of two pigments, it is a curve in RGB space. This is different from linear mixing of two pigments RGB colors using digital linear mixing model, which is just a straight line in RGB space. Given such painting image, we may want to enable editing operations such as recoloring, copy-paste delete, edge enhancement, and so on. We reversely decompose the painting into several multispectral primary pigments and their corresponding per pixel mixing weights based on Kubelka-Munk model. Then we can edit the painting in pigment space easily. The pigment here is not actually RGB colors, but several multispectral absorption and scattering curves. There are several previous works focusing on digital palette-based image decomposition and editing. 2016 is most related one with our current project. All these works are based on digital palette color compositing model, such as alpha blending, additive mixing, and Gaussian mixtures. Ours is based on physically inspired color model. There are also several works focusing on Kubelka-Munk model's application in image editing, pigment identification, and so on. Mac 2017 is most similar work to our work. It is contemporaneous with our work. They use a 3-wavelength watercolor pigment database from previous work to help extracting the watercolor pigments, assuming varying pigment thickness on the canvas, while we evaluate our approach with opaque acrylic and oil paintings and compute an 8-wavelength constant thickness decomposition of the image. Our input is a digitized physical painting RGB image I. Our output is some primary pigment H, which concatenates absorption and scattering variables together, and the per pixel mixing weights W. W multiplied H is a total images per pixel mixed pigment parameters. The relationship is modeled by such equations. We have two assumptions to simplify the model complexity. First, we assume the canvas reflectance eta equal to 1, which means canvas is pure white. We also assume the pigment thickness T over the canvas is homogeneous with value equal to 1. The thickness in the model is a scale factor, so set to be 1 did not influence the correctness of model. Changing the constant thickness to another value is equivalent to uniformly scaling all pigments absorption and scattering values. After we fix these two variables, then our model is only related with mixing weight W and the pigment parameter H. Then we can solve these problems using a nonlinear least square optimization. But this is an under-constrained optimization, since unknown variable number is much larger than the knowing equation numbers. And there are two additional challenges hiding in this problem. First challenge is metamerism, which means the different high-dimension spectrum can be rendered into same 3D color. It is useful for color reproduction on device screen. However, it is not good for reverse engineering works that want to reconstruct the spectrum from RGB color. However, when we observe these ground truth pigments absorption and the scattering curves, we can find their spectrum is smooth across wavelengths. Also, we find the division of two parameters should be smooth also. This division is an important variable in Kubelka-Munk model, which is related with pigment's mass tone color. We can enforce these three curve smoothness during the optimization to regularize the spectrum shape. This regularization is useful for solving metamerism problem. The other challenge is larger solution space. For such 4 color points far away from color space boundary, suppose they are mixed with 3 prime pigments. The triangle gamut H is ground truth gamut. However, any gamut scaled or rotated from H can be the new valid gamut for these 4 points, like H1 and H2. If color points are close to color space boundary, such gamut Q is already close to boundary in the bottom row. The scanning and rotating of ground truth gamut Q may be out of boundary, which means such gamut Q and Q2 are not acceptable for such a point distribution, which is more restricted than top row situation. Such gamut problems is usually solved by non-negative matrix factorization optimization. The initial value is important for such optimization work. Here is a simple example to show good initial values are important for optimization. The black dots here are ground truth pigments. The purple dots are other prime pigments that can reconstruct blue dots inside. The red dot means good initial values of optimization. The red gamut will gradually move to the gamut with black pigments, not the gamut with purple pigments. Directly solving this optimization with those regularization terms is still hard for whole image in terms of performance and convergency of such a non-convex problem. It is better to divide the problem into 2 subproblems. First, we can extract primary pigments from the image, and then fix the prime pigments, then extract the per pixel mixing weights. First, we introduce pigment extraction step. We use 10-2016 simplified convex Hall method to extract a small size RGB palette. We search a database to find the closest RGB entry in database for each RGB palette color and return corresponding pigment parameters as our initial pigment H0. We use a multispectral pigment database from Okumura 2005, which contains only 26 acrylic pigments, absorption and scattering parameters. We interpolate every pigment pairs by half-half mixture to expand the database. We do not want to recover pigment from whole image pixel colors. We only use image's original convexo vertices as representative colors of this image, since these vertices form the gamut shape of the color distribution of the image. Then we solve an outletting nonlinear least square optimization to extract pigment parameters with the help of pigment smoothness regularization term. This is actually the only stage of the algorithm that uses absorption, scattering, and division of absorption and scattering smoothness term. Finally, we will get the final multispectral pigments H star. After we extract the primary pigment parameters, we will fix it and solve per pixel mixing weights for whole size image in a coarse to fine manner. We downsample the image into different resolution at the smallest resolution level. In our case, the criteria is that one edge of image is below 80 pixels. We will solve the optimization with mixing weights spatial smoothness term and the mixing weight sparsity regularization term. We choose binatural grid smoothness because we want to keep the edge structure of the paintings. Refer the details in our paper for two regularization terms. After we got the mixing weights at the lowest level, we will upsampling the mixing weights and feed it as higher levels initial value of the optimization and solve optimization at each level. Finally, we will get the original resolution mixing weights map. Here are our results for multiple images from left to right. There are the original image, the reconstruction image, and the error images that is already multiplied with scale 10. The extracted pigments colors and their mixing weight maps. Because our pigments are multispectral, we show them as RGB colors rendered on a white canvas with unit thickness. Here is comparison with the layer decomposition of TAN 2016 and Axoid 2017, and with the palettes extracted by Chang 2015. This apple painting was painted with exactly 4 physical pigments in real world. Our results match ground truth pigments, and the reconstruction area is very small. When constrained to 4 colors only, TAN 2016's method has very high reconstruction errors. To match our reconstruction error, TAN 2016's approach is to use more colors. Axoid 2017 approach extracts layers guaranteed to have no errors, but the extracted layers are not composed of a single color. Instead, it is a color distribution for each layer. Chang 2015 used modified k-means method to extract a palette whose size is also chosen by the user. For this example, Chang's method cannot extract the glowing ultramarine blue pigment, even for a very large size palette. We compare our model's recoloring results with digital color mixing based recoloring result. We use our palette's RGB color for layers in TAN 2016 for direct comparison. In the cat painting, our mixing weight map for the blue pigment is sparse, and therefore the recoloring effect is localized on the body of the cat. The weight map from TAN 2016 is not sparse in the background area, resulting in some undesired recoloring artifacts. For the rooster painting using our Kubelka-Munk model, more vibrant green is obtained from mixing yellow and new blue color in the circled region. Here we compared our Kubelka-Munk model-based recoloring result with Poldov model in TAN 2016 and Gaussian mixture model in Chang 2015. To be a fair comparison, each method extracts its own palette from the input image, so we attempt to mimic all the results as close as possible. TAN 2016 suffers from lack of sparsity, while Chang 2015 has local colors artifact, as pointed by red arrows in images. Based on our results, we can have various applications in pigment space beyond RGB space. Different from only changing pigment colors to enable painting recoloring, we can also adjust the mixing weight value of a pigment to create recolored painting that would be difficult to reproduce using the features of digital image software such as Photoshop. Top is scanning mixing weight map of yellow pigment. Bottom is scanning mixing weight map of the red pigment. This recoloring is more paint-like editing on the real-world physical paintings. Adjusting the relative weights of black and white pigment is akin to adjusting the brightness and contrast of an image. The result of increasing the black pigment weight is more like emphasizing shadows and details from the image, instead of just darkening the image globally. while the result of increasing the white pigment mixing weights is desaturation of the image colors. Left bottom is increasing all pigments mixing weights, which obtain painting's mass tone colors, which is unique operation from the traditional Photoshop editing. Right column is using Photoshop to manipulating the RGB image brightness changing globally. Our multispectral CAM model results also can enable more paint-like editing, such as pigment scattering changing. For this example, green pigment scattering is changed. Increasing pigment scattering means that more light will be reflected back. So in some sense, this is similar to brightening the green color and making it more opaque, while decreasing scattering creates a darker green that absorbs more light than it scatters. So perhaps more like a stained glass. Mask selection in paintings can be improved by optimizing on mixing weight map of a specific pigment layer, instead of optimizing on RGB image colors. On top example, grab card is performed on mixing weights of red pigment. On bottom example, grab card is performed on mixing weights of black pigment. Both results are better than grab card result on RGB image. For fair comparison, no scribbles are provided for grab card algorithm. Here are some results of a copy-paste in pigment space. Each of these classical paintings has been modified by selecting some set of pigments from a region of pixels and adding them as a new layer on top elsewhere in the image. While the pasted regions are not identical to the copied region, similar to standard RGB editing. However, they appear as if they were painted as part of the image originally, if you do not know the original painting. The first stage of our algorithm can also be seen as yet another method for extracting a small palette from arbitrary image, not necessarily of physical paintings. Here is palette summarization applied to photos as compared to Tan 2016, Adobe Cooler, and Chan 2015. It is clear to see that Chan 2015 and Cooler attempt to find salient or meaningful colors in some sense. Tan 2016 and our work focus on colors that reconstruct the image. We achieve similar palette to Tan 2016, but as we showed earlier, our reconstructions have much lower error for the same number of palette colors. Here are palette summarization of Van Gogh's painting arranged by year to show the style evolution. Two conclusions are clear from this analysis. First, the range of colors that Van Gogh painted with over the year is expanded over the 1880s, as we expanded from 8 pigment to 10 pigment to achieve our good reconstruction errors. Second, the pigment color vibrancy increased dramatically over the years as well. Our weight map can improve edge-based image analysis. We apply an existing edge detection method to each weight map separately and merge the per pigment response using the per pixel max operation. Edge images can be used to adapt standard image processing routines to be paint aware. For example, we do edge enhancement by increase the thickness of pigments near the boundary according to the edge response, which can visually emphasize painted object in a different way than RGB edge enhancement. In conclusion, we provide an efficient optimization framework to extract multispectral pigments and their per pixel mixing weights from given single RGB painting image. We can enable many paint-like edits of the painting, which are beyond RGB space. Our discussion of gamut problem and several regularization terms used in our optimization are useful in other similar problems. There are some limitations in our project, and we have some future work to extend. First, using prior acrylic pigment database as the initial value may cause overfitting problem. However, we don't have other datasets to verify it, like some watercolor pigment. We assume constant paint thickness to simplify optimization. However, in the real world, this is not valid. We may want to estimate pigment layers instead of just mixtures. Then layer order is needed. Using our decomposition result to help her extract brushstroke level structure from painting image is also very interesting. Here are our contact information and the project website. If you have any questions and suggestions, please contact us. Thanks for these artists for providing great painting materials for us. Thank you.